Hello and welcome to this webinar, Making Certifiable AI a Reality for Critical Systems, with a presentation of the SAFEXPLAIN core demo. This is the fourth webinar in our SAFEXPLAIN webinar series. And if you missed the last three webinars or want a refresher of the content, please visit our videos and demos section on the website, where we have more information about each of these webinars. So before we begin, I just want to inform you that the session is being recorded and will be used on our website in the next few weeks. So you can consult it later on as well if you have any more doubts. So today's webinar will include presentations from two speakers. We'll start with a short overview of the context in which the SAFEXPLAIN project finds itself. And this will be given by Carlo Donzella from Exida Development. And then we'll have a more in-depth presentation of the SAFEXPLAIN integrated platform by Enrico Mezzetti from the Barcelona Supercomputing Center. So I'm going to give a quick presentation of these speakers that we have today. So we have Carlo Donzella, who has 40 years of experience in research and development and innovation management, project management, and quality assurance in the digital technology sector, with applications across multiple industries, especially in mobile, transportation, automotive, and media. He is the co-founder and CEO of Exida Development and other companies affiliated with the Exida Group. He is ASPICE Principal Assessor with Hardware, Machine Learning, and Cybersecurity Qualification Extensions, and Certified Functional Safety Expert and Cybersecurity Practitioner, board member of Spin Italia, team leader in the SAFEXPLAIN and Edge AI Trust projects. So we are in very good hands today. And we also have Enrico Mezzetti, who is the group leader of the Software Dependability for Embedded Systems group within the High Performance Embedded Systems Lab at the Barcelona Supercomputing Center. He holds a PhD in computer science from the University of Bologna on software timing analysis and industrial development process. He authored more than 60 publications on the verification of critical embedded systems, specializing in timing, characterization, and analysis of multi-core systems, RTOS, and software architectures. So I'd like to thank these speakers for joining us today, and we will be welcoming questions. Please go ahead and use the Q&A chat, and I will be monitoring it and sharing the questions with the presenters at the end of the session. So without further ado, Carlo.
Okay, thank you. I hope that you can hear me well. And thanks for the nice introduction. And I'm taking the first part of this presentation, the shorter part, because it is more on the context and on the business aspects, exploitation aspects of this project. This makes sense now. The project is close to its end. And we already had a webinar in the past where even recently we were still talking about what we intend to achieve in the future or near future. Now, basically, we are really close to the end in September. And so we really wanted to present what we have already at hand and close to full completion. And in that context, it makes sense to have also this sort of exploitation-oriented introduction. And I think that the title is actually capturing the essence of what we want to do. So making certifiable AI a reality for critical systems. And this is embodied today in what we already have as major exploitable result, even few months before the actual closing of the project. And so please, next, Enrico. Yes, we have already started very recently, a few weeks ago. We had a major presentation during a conference in Italy, Automotive Spin. And in that context, we actually selected one of the three industrial sectors that we are covering, automotive, because as the title itself suggests, it was mostly oriented towards this community. But we also insist on the fact that The automotive user case, that is one of the three user cases that we are going to cover in the project and also to cover today in the more technical part. The automotive case is the one, in a sense, that is the most interesting from a narrative point of view. What I mean by this? I mean that the fact of the autonomous car now are so ingrained in the mindset even of non-specialists, and this is due to the fact that, of course, passenger cars are in the mind of everybody. You do not need to be a specialist. And so what happened also in terms of debate, in terms of adaptability, acceptability of autonomous vehicles is actually a very good example of why we would need this certifiability for AI. So the fact that these first slides are mostly oriented towards automotive is not because we believe that automotive is more important than railways and space, but simply that has captured more attention, and at the same time, it is the one that is most hotly debated, and we think that we can contribute to this debate with facts and not just opinions. So, to go specifically to the point, well, I think it's worth mentioning that automotive is one sector with a very long tradition, as well as space and aerospace and railway. But until recently, compared with these two others, but also in general with other areas like consumer electronics, telecommunication, and so on, it was considered a sort of sleepy sector with not much innovation, mostly just a very consolidated sector with a mass of traditional standards for quality, production, traditional methodologies, and so on. Then, in 10 years, there was a revolution, a real revolution. And we as my company is mostly following this area, and we really have witnessed year by year, month by month, this revolution. And I want to mention, to me, it was important because there was a sort of, when you have a special event that is a pivot. And I remember that I was there at the Automotive CIS conference in Berlin, slightly more than 10 years ago. And there was, during the opening speech, this announcement from the director of VDA, and VDA, you know, is one of the most important association of vehicle manufacturers in the world. It's German, but in this field, Germany as a lead. And there was this announcement that the car of the future would be electric, connected, and autonomous. And this was a sort of very revolutionary statement. Now, I mean, it seems so obvious that there is no need for making a big announcement about this. But 10 years is at the same time a long and not that long period. In fact, can you please go to the next slide? Enrico, yes, please, thanks. And the evolution of the technology in car has a very long but not linear tradition. And in fact, if we are stunned by this, what happened in these last 10 years, well, if we go back a bit in this relatively long history, we also find something which is surprising. The first electric vehicle, the first patent was in 1890. The first electronic part in car was in 1912. And then we have, of course, other moments where there were revolutionary moments. The first airbag was in 1970, the first micro in car in 1978. The first ADAS, this is coming to closer. I mean, the first ADAS is something that is part of this revolution because semi-autonomy is actually made through a bundle of coordinated or less coordinated ADAS function, assisted driving function. And this is, again, in 1995, there was already the first one. And as I said, we insist on car, but we could do something very similar also for the other sectors. And just as a curiosity, but here again, something which is really curious, the first plane autopilot was in 1912, and it was completely mechanical and based on gyroscopic adjustments. So just to say that this tradition of innovation is very important in all transportation areas, especially automotive, but it is not linear. Next, please. Okay, now where we are now, the point is that in this mostly last 5 years, we have seen an increased polarization of opinions, even in experts. And this is really particular for car. This is why we have, say, pinpointed cars instead of, say, aerospace or railway sector as the point where we think we can make really some difference. In the sense that, of course, this discussion about the level of autonomy, the use of AI-based solution in critical systems, that means basically safety, critical safety, and also security critical system. But let's not complicate things too much. Let's skip to safety. And we know that we have a sort of two extremely polarized opinions, where even people that initially were more, say, amenable to some nuanced position, now they have split into two completely opposite camps, where it seems that it is in a sense fun, but sometimes it's not fun because, I mean, there are death threats. There are people that are considered gurus in this field that have to go around with armed escorts because they are continuously threatened by people of the other camps. And the two basic position is that on one side, I mean, of course, I mean, full autonomy is already here. I mean, we can show you, we have tons and tons of videos with incredible, say, performances. It's pure science fiction, which is just constrained by stupid considerations. Okay, you go on the other side and you have exactly the opposite. So tons and tons of videos of showing cars running over children and other awful situation of batteries in flames, engulfing entire highways and so on. And of course, this is the beginning of the end. Please close everything because before it is out of control. It is really something which is purely beyond scientific debate. So we believe that even, of course, SAFEXPLAIN was not about entering into this debate, but say modestly, we have some solutions both on terms of standards, on terms of methodology, and on terms of supporting technologies that we can say that there is a possible position which is not simply a compromise position. It is not the simple middle way, but it is a strongly argumentable middle way saying that you do not need to believe to one of these two extreme camps. So please, next, Enrico. Okay, so the idea is that we have started by analyzing well-known and maybe from this point of view not much controversial AI challenges to common practices for fuzzer-related software, including failure rates that are used for software design, and a very long list of well-known and documented in literature, in technical literature issues. We have set a number of goals and results. Some of this will be presented more specifically by Enrico. And just to mention three big, say, abstract, big high-level areas. So make ML, machine learning and deep learning components explainable and traceable by design. The other one is adopt the FUSA standards to allow qualifying and certifying of this kind of software. This was one of the biggest challenges also because the landscape of these standards is moving extremely fast. So for instance, when we started, there was no official standards already covering this in detail. Now we have at least 8800 that was recently published, and it is specifically addressing this. So also we are monitoring very strictly this. And last but not least, all this by preserving sufficiently high level of performance, because otherwise, I mean, you may have this ideal world, but unachievable with, say, current software and hardware technologies. So the SAFEXPLAIN results could be, we believe, are the basis for a very reasonable third position. So we already know that low, mid, and high safety ADAS function that are anyway the skeleton for any semi-autonomy or full autonomy can, and in some cases have to be implemented with machine learning and deep learning solutions. There are no other, usable and simple and effective solutions. But at the same time, this is not just a green light for Far West. It is, we need new and updated standard and regulations on quality, safety, and security of AI to qualify and certify new solutions before they hit the road. Of course, also after they hit the road, because also during operation this is very important. But it is also very important that we do not go into manufacturing and in operation before having significant qualification from this new or updated standards. Please next, Enrico. Okay, very quickly now we are going a bit more into the what is the project about. I'll go quick because I do not want to eat up on Enrico presentation, which is the most interesting part from a technical point of view. So the critical embedded system and AI, we have AI techniques that are very, very relevant. For instance, object detection for transportation is really a basic things. Tracking, path planning, driver monitoring systems, and in fail-safe system, as all the critical transportation systems are in this case, all these aspects are something that for which the traditional approach for qualifying and certifying software and software-based solutions are weak. So the real challenge is that AI software development does not adhere to the traditional process for deterministic software because it's based on empirical basis, especially one of the biggest points is number two. It's very heavily data-based. We know that the new standards are devoting big sections to the aspects of the quality of machine learning and data learning data. It is not correct by construction as we expect from traditional software, and typically it is based on a monolithic architecture. Next, please. Okay, so in this case, just to go to the basis of the project has the ambition, and we think that now we are already at a stage where we can claim we have largely achieved this ambition of architecting solution enabling certification of qualification, because we can adhere to the safety culture, which is not a generic term, but it is a concept which is well defined even in traditional safety standards. We can preserve the high performance that is anyway needed to have, say, useful solutions. And it is so flexible that we can adapt to many different cases. In the project itself, we have 3 demos. We are going to have 3 full demos soon, but we have already examples in cars, railway, and aerospace. But we trust, and we have also good argument to say that this can be extended to adjacent sectors. Next, please. Okay, so this is my last slide. And so we have both a platform and a toolset support for AI-based critical systems. And we had multiple requirements for platform and toolset. We had the development of AI-based critical system. So a number of requirements coming from the fact that this platform and toolset has to support this development. And the hardware platform, we didn't work on the hardware part, but we had to select and configure the hardware platform. So in fact, even if we do not work directly with hardware, we needed to have competence and ability for choosing and configuring. Support for the famous V&V approach, the verification and validation that everybody in functional software, in functional safety knows well what it means, and provide a standardized interface for the development and integration of the diverse use cases. And now I think that from this I can pass over to Enrico.
Thank you, Carlo, for the introduction. So yes, I will be going over a bit more after the motivation of the overall motivation of SAFEXPLAIN project. I will be diving a bit into the technical details on several aspects in the project. So ideally, everything on this webinar will be trying to provide all the necessary understanding to follow what will be actually the core of the presentation, which is the core demo. So first of all, I will be going over a bit the SAFEXPLAIN landscape, technological landscape, what we are covering, what are the main elements that are being embedded into the overall SAFEXPLAIN solution. Then I will be providing an overview of the platform integration that we have on top of the hardware and software execution layers in order to support these methodological and technological building blocks. And then I will provide a view over some examples that we have in what we call the core demo of SAFEXPLAIN. And then I will close with some final thoughts and remarks from the project. So moving to the landscape of SAFEXPLAIN technology, I think this part is necessary. As Janine was mentioning at the beginning, this is the 4th of a series of webinars. So some of the aspects are going to be only mentioned here. If you are eager to get more details, so you can always get back to SAFEXPLAIN website, and you can retrieve the past webinars there. So SAFEXPLAIN as a project has a distinguishing trait. The distinguishing trait is that it's providing not a specific solution for one of aspects, but is providing an holistic approach for the deployment of safe and explainable critically embedded system with AI. And so the solution that we are providing in the project are covering different aspects, from process and procedures that we deployed to the design phase of the system and of the software, and to the corresponding analysis and support at runtime. So the main building blocks here provided by SAFEXPLAIN is the definition of the safety life cycle for the system and software development based on aware of the DL element, machine learning element, including the system, deploying the system. Then we have the definition of safety, functional safety compliant architecture for deep learning based systems, and the integration of what are the explainable deep learning, explainable AI technologies on top of this system, and everything, of course, these aspects about the life cycle, the architectural part, and the different techniques for the AI need to, rely on generating a set of requirements on performance, predictability, AI library support, configuration, execution platform, and so on and so forth. That those set of requirements are captured by the execution platform, which is the combination of the hardware and software layer that are kind of meeting the requirements coming from the other building blocks in the project. And is capturing all these requirements about a set of technologies and tools that are fully integrated in a common layer. So all the requirements stemming from the methodologies are met through the execution platform, and also all the technological solutions are deeply integrated and can interoperate in a smooth way. And of course, the demo also is the baseline for the demos. As Carlo was mentioning, we have the core demo, but we are also, as an outcome of the project, we have full demos with the different technological domains that we are covering. So first of all, to giving the premise on the safety life cycle, SAFEXPLAIN is proposing AI FSM. So AI is FSM is an extension of traditional functional safety management, which is covering the management of all the essential activities in functional safety life cycle of a system and software, according to IEC 61508. All these definition of the steps and phases in the process are meant to prevent error in the specification, design, development, manufacturing, commissioning, decommissioning of a software system. So we have different phases that are part of the standard definition of functional safety management, and but we had to kind of merge this view of functional safety management with the AI management model, which is its own step from the requirement certification on the data and the model itself. And we have data management, training, verification of the model, and deployment. So the proposal in SAFEXPLAIN is functional safety management extended to cover AI aspects. To do that, we have sometimes the extension of already existing steps in the process, in the phase V-shaped process. For example, we are extending the definition of the requirement phase in order to capture requirement of the data and the model itself, or on the integration and validation. But we also have specific new phases that are generated by in order to capture the requirement from the AI part. So in particular, the data management phase, in order to cover the data requirement specification, collection, preparation, and verification. This is a very relevant part nowadays in current standard, trying to capture the AI features. And we have also the learning management phase, which is instead focusing on the starting from the collection requirements on the model, so the design of the model, the training, the evaluation, the verification in a loop. And finally, with the inference management phase, which is more related to the deployment of the model. So it deals with the optimization and transformation and verification of the model before deployment. So by defining this AI aware functional safety management, we are enabling the deployment of explainability AI solution in order to support the different phases that we've been identified, and also to support the verification and validation of AI system in functional safety critical scenario. On the architectural level, we are extending again traditional functional safety concepts. So the traditional functional safety concepts are deployed in order to capture random and systematic faults. This is done normally by mastering the complexity that on the hardware and software ledger that emerges on the platform by in advocating some well-known principle like segregation, support for miscriticality, controlling the usage of different resources in the platform and in the software layer. And even in this case, we are adding some capturing some specific traits from the AI and deep learning. So in order to capture what can be the model insufficiencies at the deep learning level, and also to integrate explainability solution. So normally we have different type of architectural archetypes that cover the high-level architecture and low-level architectural design, like well-known concept like redundancy, diverse redundancy, the inclusion of supervision elements in the architecture, and the introduction of in deployment of different layers for diagnostic and monitoring of the system at runtime. And the overall strategy here in the project is in order to capture AI-specific traits, in order to deploy methodologies and solutions in order to reduce the uncertainty coming from the models, and to acknowledge and account for the residual uncertainty at runtime. So from a practical perspective, this functional safety architecture is a definition of different elements that are then combined in a set of predefined safety patterns. Safety patterns are incremental architectural patterns that are addressing the deployment of AI-based subsystem within a functional safety critical system. We have this is done incrementally, so we have different safety patterns that cover different aspects from, for example, the simple scenario where AI subsystem is not contributing to safety-related function. So it's like a sandbox taking care of different aspects that are not critical to the functional behavior. In this case, from the functional safety perspective, we have the traditional functional safety elements, and also that are also compelled with the complexity coming from the need to integrate this system on relatively complex platform in order to achieve the performance requirements that are coming together with its complex AI functionalities. Then we have a safety pattern that instead sees human-machine interaction, where the AI subsystem is not directly contributing to the functional safety critical function, but is contributing in some way to the decision-making process. So in this case, we complement the traditional functional safety aspect with AI performance insufficiency and functional safety risk factor. Then we have the third safety pattern, where we have the fully autonomous system, where actually the AI subsystem is contributing directly to decision function. And we can cover this in this way, an incremental integration of the AI functionality, and we're building with a software and explainability AI solution, covering the hardware software configuration and enable runtime monitoring with timing aspects and non-timing aspects in order to, as I was saying before, reduce uncertainty by design, but also acknowledge and account for residual ones at runtime. On the explainability AI perspective, so we are capturing, allowing the deployment of explainability AI techniques on the different, within the different phases of the AI FSM, on the data management phases, with data explainers, for example, and on learning management and inference phases with a model explainer, in order to explain the design, to reduce the epistemic uncertainty for the model, and to regulate the inference verification. This, of course, happening at the level of the system at the design time. And we have been building a set of tools and libraries in order to cover these aspects that can be deployed on top of our platform. But at runtime, we have the deployment of specific techniques, especially that are instantiated into what we call the model supervisor, with the supervision block taking care of intercepting the anomalies on the model related to input anomalies, model anomalies, outcome anomalies, or execution out of operational design scenarios. And definition, for example, for a surrogate model for consistency checks on the outcomes of the model, and to provide an uncertainty estimation that can be then used by the decision function together with the prediction of the outcome of the models in order to provide an output of the ensemble of models, and together with a trustworthiness score that can be used in order to take a decision. All these are coming from the SPLib, that was the tool I was mentioning before, but implemented into a DLlib tool, which is a set of libraries that can be deployed at runtime. And all these are the main elements in the building blocks. As I was saying before, if you need more details, you can go back to the previous webinars in the series, and you also can contact us directly. So when coming to the integrated platform is a set of elements of tool. As you know, we have a set of requirements I was mentioning before, coming from the deployment of supporting the AI ISM at runtime, deploying XAI solution, enable verification validation support, and capturing timing concern in safety critical system, and guide and provide guidance for the hardware and software configuration. All this in the project is captured by a middleware layer that provides an ideal playground for the integration of different methodologies and tools. First, a brief overview of the platform. Other platform, as Carlo was mentioning, we didn't go for a custom hardware. We took a reference COTS hardware platform, NVIDIA Jetson AGX Orin, with enough computational power in order to deploy AI-based functionalities on the edge. It brings 3 core clusters and then an Ampere GPUs, and also includes a very specific ad hoc accelerator for deep learning, the DLA, and for vision, the PVA, for example, that can provide improved performance with limited power consumption. And on top of that, we have the reference software stack. As you know, the NVIDIA target comes with an adapted version of Linux environment with a Ubuntu 22.04 in this case. And that was ideal in our scenario in order to support the different libraries and tools for the deployment of AI-based application. And of course, it also ensures generalizability of what we are providing as a platform. So the middleware concept is, as I was saying before, deployed in order to capture all the requirements that are coming from the different methodologies and the application, and to make this compliant with the hardware and software layer. So we are deploying this middleware layer, which is based on ROS2, and is meant to capture the requirement both at design, development, and testing, and at operation. In the first case, by ensuring the deployment of safety patterns, so these architectural constraints, and to support the verification, and at operation to enable the runtime monitoring and support the deployment of the explainability AI solution. So we build on ROS2 because of the widespread adoption of this framework. Is a well-known communication framework for a distributed system. So it allows for a modular design scalability with a very clear semantic with publisher subscriber, and also comes with some nice features for support for functional safety and VNV activities like Health Manager and automation for software testing and so on and so forth. So the middleware allows for provide a set of nodes that are predefined, and that comes with a very specific communication pattern with a bespoke monitoring mechanism, and with a simplified semantics, so that it's easy for an end user to come with the application and to redeploy the application using these nodes. The main concept for the safety pattern, that with the safety pattern we are providing compliance with the middleware. We're providing compliance by design with the safety pattern while preserving the modularity of the application. So we are going to have a set of mandatory nodes that are meeting the requirement for the safety pattern in terms of monitoring and supervision, for example. But we also can have support for ad hoc nodes in the application. And this in order to facilitate the integration and BMV support and integration of the technology. So needless to say that safety patterns are also amenable to model-driven engineering approach, which is also sought features in the safety in embedded safety critical systems. Just to give you a concrete idea of what can be the deployment of a safety pattern on top of the middleware. So let's focus on safety pattern 2, which provides a middle ground idea for the integration of the technologies, where the AI has a middle ground role. So we have the identification of traditional subsystem and AI subsystem, which is the main focus for us now. On top of the middleware, we have, according to the SP2, safety pattern 2, we have diverse redundancy by deploying 2 different models covering the same functionalities with the diverse. And all of them have supervision blocks with taking care of standard functional safety diagnostic and monitoring activity with the L1 diagnostic and monitoring, and more AI-related supervision functionalities on the model. And the outcome of the model and supervision blocks then are redirected to the decision function that can take a decision based on the ensemble of the 2 redundant and diverse models. And together with the outcome of the L2 diagnostic and monitoring, which instead capture diagnostic at the system level, can contribute to the actual decision part, autonomous decision making, which is taking the safety control that elaborates and sends a message to the actuator. And we are deploying on this pattern functional safety solution on the L1 and L2 diagnostic and monitoring layer, more traditional ones, and explainability AI solution in the supervision blocks, in the decision function, and in the L1 diagnostic and monitoring layer as well. And safety pattern tool essentially provides like a skeleton where the user can plug in functional and semantically relevant code for the ML AI components, supervision component, decision function, and control logic. So it's very amenable to tailoring and adaptations. We're also covering, as Carlo was mentioning, hardware and software configuration aspects in order to comply with the timing requirements coming from the functional safety critical domains. So there are well-known concept of freedom from interference in automotive and control of interference channel in the avionics domain that trying to capture the variability and interference coming from the execution of multi-core systems on top of multi-core systems with a wide range of shared hardware and software resources. And the configuration here is meant to promote segregation while meeting performance requirements through different identification of what are the bottlenecks in the platform that can be found different layers in the architecture and different components, and trying to deploy and exploit what are the available configuration options at hardware and software layer to define a set of predefined configuration that the user can adopt and deploy on his system. And this is done by working again at the level of the safety pattern. So we are playing with what we have in the actual platform we are considering. For example, in the horizon, we can play with the power modes control. We can enable partition in several resources. For example, the L3 cache, which is shared across clusters, so is an important source of timing interference. And we are playing with how the safety pattern and the nodes are mapped into the underlying layer at the hardware level. So we are capturing the nodes at the middleware layer, how they map to the executors at the ROS2 layer, and how these executors are then mapped to the thread level and process control in the Linux layer. And then we are mapping them to the kernel, to the kernel parameters and the RT patch in order to further reduce the variability on the platform coming from the OS. We are covering the time localization aspects, in this case by providing probabilistic time analysis techniques on top of standard approaches. This has been increasingly considered in order to capture the variability that arises as a combination of the complexity of the hardware system and the functionalities running on top of them. And it's a kind of an alternative and complementary approach to more traditional time analysis approaches. We use a specific method based on Markov's inequality here that is fit in order to capture the time distribution of AI-based functionality, which normally exhibit a kind of mixture distribution that are not easy or cannot be captured with more standard probabilistic time analysis approaches. And we are building this, of course, we are able to deploy these methodologies by enabling an observability layer on top of the platform. So we have a specific library called BMEOlib that allows to capture timing-related events, as well as a set of hardware events in supporting and fully integrated in the middleware. And the other second most relevant aspect from the timing perspective is capturing the residual interference. As you know, we can capture some of the sources of interference by playing with the other software configuration and by deploying the safety patterns. But it's practically impossible to achieve a full freedom from interference, in this type of platform. So what we are doing here is to provide a kind of safety envelope for the timing behavior of the system. So we are capturing interference when this interference until time exceed a predefined threshold. So ideally we can separate, we can cluster the application. We have the system in critical task and non-critical task. We can define a threshold for non-critical task of usage, for example, of the bandwidth on a given hardware resource. And we can monitor the usage and capture whenever a non-critical task exceeds its quota for usage of a managed bandwidth. And this is done on top of the middleware itself. And whenever we intercept bandwidth threshold exceedance, we can prevent the non-critical task from bringing more interference on the critical one by making it throttle until the critical task terminates its execution, then resume with the non-critical one. We're also providing platform support level for VMV. We are building a lot on available elements in the tool chain, and for in the ROS2 also functionality with the launch for the environment and configuration of the middleware, and ROSback to replay data during testing phase. And we are also collecting all the runtime monitoring logging that is allowed by ROS2 and also by integration of our dedicated PMU library. Also, explicit support provided for the scenario-based strategy for verification and validation. So we can specification of triggering condition, test specification, and test matrix for the different domain. We can support this on top of the middleware by controlling the input stream and the configuration and checking for the triggering of a specific scenario. So just to a quick recap before entering into the practical example that we have for the core demo. So we have a set of requirements that are coming from the different building blocks in the project that are being integrated on top of the platform. They're coming from specifically from the definition and configuration of the hardware software layer in order to comply with the requirements coming from the AI FSM. So we have the definition and enforcement at design time of the AI safety pattern, and providing support for the automated testing and BNB on top of the middleware layer. So we are enabling runtime monitoring for all the different diagnostic layers we have in the system. And we are promoting the deployment of this safety pattern. In this case, we have diverse redundancy with definition of different building blocks for the supervision and decision function, where we have the ability to deploy specific libraries for explainability and specific methodology for the timing characterization and control of timing interference. So I see it's a very wide support. We have at the platform level in order to capture the different aspects. We have for the IFSM, for the explainability AI, and for also in order, as I was saying before, it's important here, but it's also important to have to guarantee enough requirement for the system performance to meet the minimum threshold for the AI functionality to have to fulfill their goal. So what is the core demo? The core demo is essentially an adaptable cross-domain demonstrator is a simple example, small-scale, simplified example of an integration and deployment of all the technology and tools we have been developing in the scope of the project. So it's a set of replaceable and configurable building blocks that can be deployed in a specific scenario in order to showcase specific features of the system, for example, specific features of the models, specific features of the explainability AI technique that has been implemented in the supervision function or decision function, and the logic that can be implemented, for example, in the L1 or L2 diagnostic and monitoring layer, as well as to support and simulate execution of relevant scenario for scenario-based testing. So the SAFEXPLAIN core demo is a configurable set of elements. Of course, we have in the course of the project, this is not covering what is instead the full demo. The full demo is an extension and a rich version of all these functionality that are combined together. But we developed example for the core demo for the 3 different domains we have in the project, for the automotive and space and railway. Now we are going to give you a brief view over the execution of this example, at least in a couple of domains for the sake of time. So we are going to provide some details now on the space example. The space example is the example that's been developed more in the scope of the SAFEXPLAIN, and it's essentially modeling a satellite position tracker subsystem, where is taking care of the identification of the satellite and the space in a very harsh condition for the lighting condition. It's a small scale and simplified version of the space use case, which is instead termed full demo. The full demo is taking care of deploy different modules for AI for the pose estimation. In this case, we're just focusing on the satellite position tracker subsystem, and we are deploying this in the scope, in the framework of the safety pattern 2, which was the middle ground scenario for integration of the AI subsystem. Here we have the traditional subsystem, and then we have AI subsystem, which is not taking autonomous decision, but is contributing in a sense to the actual decision process. And the core demo here, we are not, of course, in the need to capture all these elements we have in this SP2. Of course, we do not have, we can avoid focusing on the traditional subsystem. We can avoid taking care of the actuator since we are in a simulation environment. But we are capturing all the other relevant aspects in this SP2, like the diversion redundancy at the model level, supervision blocks for the supervision function and L1 diagnostic and monitoring, and the L2 system level diagnostic, and how all these interoperate for the decision function and eventually for the safety control in the decision. So the core demo space are just some elements for the understanding. For the deep learning models, we have a redundant model for image recognition. So for object detection, in order to detect the presence of a satellite in the input images, and it's specifically tailored to the space target, we have 2 different models deployed here. One is the single shot detector implementation. It's a fast model, which is using the mobile net backbone, but is optimized for the space domain. It's a single pass algorithm. Again, it's a very well-known reference algorithm for image recognition. And we are deploying it together with a faster RCNet. RCNN is the region-based convolutional neural network. Again, it's based on a single pass. It's first define different regions in the image, so it can make object detection and classification at the same time. It's a bit slower than SSD Lite, but is more accurate. On the supervision block, we have on the supervision function, we are deploying anomaly detection method for like a variational autoencoder, which is able to detect anomalies in the input provided to the model, in the model activation layers, so detecting there are anomalies in the layers that have been activated during the execution of the model, and also able to capture anomalies in the output. We can also deploy different solutions here, like a surrogate model based on random forest, or also we have an uncertainty aware model based on Monte Carlo dropout. On the decision function part, we have now we are providing an ensemble method to define a single outcome. In this case, will be a bounding box of the satellite detected in the image of the model prediction. So it's aggregating the outcome of different models and providing an explanation if there is an anomaly, and providing an indication of what is the anomaly and also the anomaly score. On the L1, we are deploying input temporal consistency, which is checking the consistency between different inputs, for example, whenever we have an anomalous distance between two input images. And on the L2, we are providing basic functionality for health status and monitoring of different components in the model. So here, essentially, we are getting an input. We are providing the input to different models. This is then also captured by the L1 and supervision function, supervision blocks, which are independently checking for some aspects in the input state and in the output of the models. And then we have this information that is rerouted through the L2 diagnostic monitoring that is provided to the decision function, together with the output of the model that is then used in order to provide an outcome to the safety control module that, together with the information on the L2, is providing capability to get the results and define an actuator command. This is on the target side. On the monitoring side, we are deploying a set of functionalities on a remote node in order not to use the computational power on the target. There we are providing different functionalities in order to model the outcome of different components, for example, for the decision function, but also of the model themselves and all the parameters and information that goes through the L1 and L2 diagnostic monitoring. This is just for showcasing purpose in order to track the execution without affecting the execution of the target. And the L1 diagnostic monitoring, I say we are deploying temporal consistency. See, we are detecting essentially whenever we have an anomalous gap between two consecutive inputs in the input streams. Like in this case, we have the distance between the second and third instance of the satellite is too large, given the frequency of the input. That may be suggesting a problem in the input sensor. At the supervision function level, we are checking, for example, different types of anomaly, and an input anomaly will be in the similar scenario to detect something that is out of the distribution of the inputs that have been observed so far. In this case, we have a different airship that is not a normal satellite, so it's being detected by the system. Going to the actual execution of the platform, now we are here showcasing what we can see from the remote node when we are executing the code and the model on the target. So the target is the NVIDIA GX remote. Here we are connecting, exploiting the ROS2 DDS layer to the platform remotely, and we are essentially we are able to deploy a use case with some scripting functionalities, so enable to trigger some specific condition on the execution. So now we are bringing up some widgets in order to monitor the execution of the system. These widgets, one of these widgets is going to capture the outcome of the decision function with the overlay on the outcome of the supervision block. And we are also showcasing the output of the two models, and we are also showcasing the outcome of the L1 supervision monitoring diagnostic and the decision function results and the alive status of the L1. So we have here, for example, the first error. The first error is an input-related error. This is not affecting the decision outcome. It's an error related to the fact that, as we said before, we have an anomaly in the input flow. So we are moving from this frame to this other frame. So there's too much time in order to move from one positional to the other. So this it detected an input error that may, as I was saying before, hint at a problem in the sensor part, but it's not affecting. Of course, you can get some countermeasure and reaction at the system level, but it's not affecting the decision outcome. In this case, instead, we are capturing an anomaly in the model level at the model level. So it's as a supervision function intercepting a problem in the model. In this case, we are capturing a bounding box ratio anomaly. It's a output anomaly here. So the output is capturing bounding box was a ratio between the x-y axis is out of the distribution observed during the learning phase. That may hint at problematic exposure of light in the image in this case. And the outcome of, in this case, we are not taking any decision because we are not actually connected to an actuator, but in principle, given the order and given the score that we are given to the other, the decision function, and in the second stance, also the safety control can take a decision. And that could be in a different scenario where this is more critical, covering a more critical functionality that can, for example, move to a safe state or delegate the decision part to the non-AI subsystem, for example. And we are still getting an example here, for example, for the same type of anomaly with a Binny box ratio. And now it's coming a different one. So we have the ability in the control with all the showcasing support to switch the input stream of the simulation so that we can, for example, try to trigger the specific scenario by just switching the sources for the models. And whenever we get an anomaly, on this case, in the model, is a different type of anomaly. It's a area anomaly. In this case, we see the satellite is the area occupied by the satellite image is too high. Is something that is again out of the distribution that is has been observed during the learning phase, and in fact is hinting at very dangerous positioning of the tracking element here. So here we have another example of bounding box anomaly. So this is related to the, so let's say we were capturing some issues at the diagnostic layer for the L1 that were related to the input, the capability with the temporal consistency in the input phase, and some other anomalies that are instead captured at the model phase in the model element through the supervision function. One was related to the bounding box, and the other one was related to the area of the satellite in the picture. So we also have support, as I said before, for the timing aspect. In this case, we have the capability in the middleware to enable time monitoring and transparently from the end user. So we simply configure a node to, for example, an ML component in this case to be monitored, and we are capturing the timing profile information on the remote node, and we are able to apply the probability time analysis by, for example, in this case, by calling a simple R script to apply probability time analysis techniques, the REST in this case, and we can also have this updated dynamically as long as the system executes and provides additional inputs for the analysis. Now we are just using the anomalous input stream in this case, but in general, this is a timing monitoring part with the offline analysis phase that can be collected during the nominal behavior of the system. So now just to provide you also a brief overview of the automotive example. The automotive example is a little bit contained with respect to the space one. So in this case, we focused on the deployment of simply one of the deep learning components. And this is in this case devoted to the detection of the pedestrian in the road, with contributed to a warning system, and in the end to issuing an emerging braking commands. Again, the reference safety pattern is still safety pattern 2, where the AI can contribute indirectly to the decision process. And in this case, at the model level, we are deploying YOLO version 11 with a pre-trained model, and we are feeding an input set of input frames derived from Carla simulator. On the supervision function for the explainability AI, we have again the deployment of a variation autoencoder. This time is trained, of course, on this different model. And while the decision function is mostly visualization driven, because we have not the need to do an ensemble of the two redundant models. So just visualize the bounding box and for detection of the obstacles on the street. And at the L1 diagnostic monitoring layer, we are deploying again the input temporal consistency method, which is still based on checking for the consistency of the sequence of images. And the L2 is capturing the basic functionality for F monitoring and status monitoring for the different nodes in the system. Here again, we are deploying on the remote node. We can script the definition of a set of widgets we want to bring up. In this case, we're going to bring up the outcome of the model, and again the monitoring layer coming from the L1 status and decision function and EL1 monitoring. See here in this case, the decision output is just for visualization purpose, but is reporting the anomalies that can be captured at the DL1 layer and on the model, but not on the ensemble of the two models, for example. So again, here in this case, we have the scenario where we are approaching a pedestrian that is in the middle of the street. At some point, we will start seeing that there is a problem in the sensor, so in the input stream, and the speed at which we are approaching the pedestrian is increasing, and it's clear that we are missing some inputs, like input error here. You can see on the terminal output. It's like we are kind of skipping set of frames in between one or two frames. In the end, we are also getting an anomaly error because of the output of the model. Because as you see in this case, we are in a scenario where the pedestrian is too close to the car. Of course, this is out of the distribution that has been observed during the learning phase. It is easy also to deploy different scenarios here. It's sufficient, for example, in this simulation environment to enforce a different scenario in Carla to get the outcome, and to a different scenario, for example, to trigger a specific scenario for scenario-based testing to get the outcome and to feed it to the system here in order to see how the system reacts. This model, core demo, can be generalized, highly generalized. See, we have this set of nodes. By definition, the middleware is fully generalized. We can have different components deployed. We can plug different models, different logic in the L1, a supervision function, decision function. At the minimum, we can reduce the core demo to a very simple subset of the elements, as was mainly done, for example, for the automotive use case. When you can bring your own model, you can bring your own decision function, you can bring your supervision function logic, and you can bring your static set of input frames. So this is easily portable to any example model you may have. And also we have this set of showcasing features that I was exploiting before. for the remote visualization of all the information on remote node without affecting execution, with a remote controller in order to control the input, the pace at which we are processing input. We can pause the input stream, we can go continuously, we can go step by step, and we can also trigger fault injection by acting on the input stream, and also by switching nodes in the component, different components and elements in the safety pattern, which is something, of course, relevant from the system perspective. And we can easily integrate a specific scenario in the demo by playing on the input stream. So just to close quickly, we are a bit late, I guess. So we have a set of tools that are highly interoperable between them. They are fully integrated on the SAFEXPLAIN stack, but some of the elements can be also deployed outside of this full environment. Some of the elements, most of the elements are highly generalizable. We have platform level support, for example. Now we have targeting a specific hardware, but the same concept apply to different hardware software setup, of course, with some limitation or even with some improvement for control on the hardware software level. Building on Frost 2 for the middleware, of course, allow some high degree of portability across different environments. We have been demonstrated the feasibility of the approach on 3 different use cases from 3 different industrial domains with different criticalities elements, with different challenges, with different domains. And we have also developed example core demos for all of these domains. And as a final result of the project, we are going to have a full demos for all these domains with a large complexity and so on, with different components and so on, with different scale. What is relevant to mention here with what we have shown with the core demos is very simple, it's very scalable, but another good aspect is that is including open source elements. So the core demo is meant to be open. Most of the elements are going to be delivered open source, are available open source, or some small proprietary parts could be delivered with free to use and fully documented. Yeah, this is just a closing slide. Carlo was going over this here. So we are the project is closing on September 2025. We are, as Carlo was saying, we are very positive of the result. I think we were very ambitious in the beginning, but we are also very satisfied at the end of the project for the technological and methodological outcomes. And we are looking for early user adopters. So the core demo, of course, is an enabler for this type of adaptation or exploration of the technologies and methodologies. And last but not least, we have a final event for the project. Is going to bring together different projects in the Trustworthy AI cluster projects. And of course, you can get more information here on the SAFEXPLAIN website or this QR code. And we invite you to join to the event. We are sure that's going to be very interesting.
Great, Enrico. Thank you very much for this presentation and for these demos. They're really looking great, and looking forward to the final event where we'll see a bit more. I see there is already a question here in the chat, so I'll go ahead and ask that to you. Are there any plans to tailor the software to other accelerators, such as those used in the automotive stream of the European Processor Initiative, for example?
Yes, at the moment. So as you were saying before, we focus on this platform. The platform indeed was already offering redundancy in accelerators. Was saying in the beginning, we have the GPU, but we also have ad hoc accelerators. And of course, this is, at least from the platform perspective, what is relevant is how to control and configure the way the application and the system and also the architecture is executed on those nodes. And there is no stumbling block was deploying this solution on different types of accelerators. It's going to affect, of course, performance and possibly the way we can share those accelerators across the different components Here, the core demo is a simplified scenario. We have two redundant models, but if you think about a more complex system, we may have, or we are meant to have multiple ML elements, some of them because of the diverse redundancy scheme, but some other because they are taking care of different functionalities. So the more options for acceleration we have, the better from our perspective. And we are looking forward for a new platform also to deploy these solutions.
Yeah, I think that we can add also that I remember that during the first year of the project, I mean, this point was much discussed at an early stage, and in fact, the design of the architecture took this significantly in consideration, and many architectural design principles were exactly based on giving the best independence from any specific hardware solution.
Yes.
So multi-layered approach and so on.
Yes. In the end, for the deployment, we had to be not fully hardware agnostic, but in principle, all the concepts, especially on the design and architecture, are quite flexible and hardware agnostic.
Yeah, so the compromise was on the practical side, not
Yeah.
on the concept side.
Yes.
I think it is significant. Yeah.
Great, thank you. Are there any more questions from the audience? If so, put them in the chat or in the Q&A, and I'll read them out loud. Otherwise, I guess I would also just ask, so the core demo seems maybe a simple piece of technology. It's all together. You have all this skeleton, but to what extent is it really representative of the SAFEXPLAIN solutions that you have?
Yes. Well, as I was saying before, yes, it's a simplified scenario where we have simple functionality and we have a simple methods or that are deployed in different blocks of the architecture. But this is indeed already representative of, for example, on the flow of the information that we are using in order to capture what cannot be captured by design. I was mentioning at the beginning of the presentation that the uncertainty that cannot be fully detached from the AI models, and all the residual risk, residual elements that we can have in the platform. This is already captured, and you can see how this can be captured already in the simple core demo. We have the redundancy. We have the multi-layered diagnostic and monitoring. So in the example here, we only have 2 layers, but in reality, we will have at least, we are talking about 4. The L0 that was not explicitly mentioned there is provided by the diversity and redundancy. Then we have L1 at the ML component level, the L2 at the system level, but we also have the L3, which is the one eventually entering into a safe state, for example, or a graceful degradation in case of anomaly. So all the ingredients of the recipe, SAFEXPLAIN recipe are there. But I invite the people who is interested to the final event, because we want to have the full demos. And the full demos are on a different scale, and you'll see how this scales. This scaling by not losing the main principle that we are showing with the core demo, but they are scaling in complexity and on diversity of the different solutions we can deploy on the different blocks.
And I will just add to this, Enrico focused on the distinction between the core demo and the final demos, but the full demos, but also specifically on the fact that demos, be they the core or the full demos, are actually a demonstrator of all the projects. So that's again something which is not trivial. Enrico, you already mentioned this, but I would like to further stress this, because all the aspects, from the methodological aspects, from the support to qualification to the say the all the explainability aspects, all the models actually coming from the use cases, and really you can find everything. There is no part of significant results from the project that are not directly represented in the demos, and which is, I would say, not that common and not that trivial.
Yes, I mean, you're right. In the demo I was showcasing before, you see the outcome, what is visible, but you cannot see, for example, details on the XAI techniques and on the techniques that are being deployed and on. And we have expert in the consortium with that, and I'm sure that we'll showcase the expertise in the final events.
Okay, excellent. And maybe just a last question about how interested audiences might get more information about the core demo. So can this be tried out? Can they ask you for some information about how to play with this themselves, or when this is a video? I mean, they can look at it, but any advice for next steps if people are interested in having more information?
Yes, so today, for safety reason, we didn't go with the live, connected to the board live, because whenever you try this, we are strict on time. It was too risky, but we have a lot of flexibility here, and the idea, as was saying before, is we are eager to have people trying out our technology, our setup. And we are also very confident that this is easy to adapt, relatively easy to adapt, to tailor to a specific use case. And we are also looking for opportunities for collaboration, because, for example, trying out this on different scenarios, different setups is also something that we want we are pursuing. And we can, I mean, for sure, there are ways to get in contact with us through the website. Any direct request for more information, we are available to the generic contacts, or you can write directly to us.
Yeah, and we can also add to this that especially between now and the end of the project, where we still have the full consortium working together with an open budget also for this kind of dissemination activities, we can also say organize dedicated calls where there is maybe a community or a small community in one of these three sectors wishing for a dedicated demo. We would be very keen on
Yes,
this.
yes.
It would be a win-win situation. We learn more about specific needs and requests, and on the other side, they would have something which is dedicated to them.
Yes, yes. In fact, we already went through a dedicated ad hoc workshop with some interested partners. So that will be the perfect way to proceed in this line.
Perfect. Thank you so much. And I see no more questions in the chat. So I think we're done for today. And stay tuned, because this video will be put on the project website, and we'll have more information. And of course, look for the final event where we'll have the full demos. And this is a free event, but registration is mandatory. And thank you so much for this to the speakers for joining us today.
Thank you all. Thank you.
Thank you. Bye-bye.
Bye. Thank you.
Pleasure. Bye-bye.